Hi everyone, welcome to the webinar on Altis Snowstream. So today we are going to see how Altis has a reusable template for ingesting streaming data into Snowflake. So we have three presenters today. So myself, Anandraj, so I am a principal consultant from Altis. So I have two other data engineers who worked on developing this tool, Mike and Andrew. So they will also be presenting part of the session. So as we will be going through the session part by part, like I'll be doing the first part and then Mike and then Andrew. So if you have any questions on the way, you can continue to ask the questions using the Q&A option in the Zoom options. So we will answer the question at the end. So we won't stop in between to answer the question, but you can continue to log the questions as they come to your mind. So let's, with that intro, let's start the session for today. So today's agenda is the problem statement behind developing this tool, why we developed this, and what were the problems that were considered in coming up with this tool. And then also we will see like how Snowflake was, what are the advantages of Snowflake, how it helped us to solve the problems stated in the problem statement, and then an introduction to Altis Snowstream, what Altis Snowstream is, what it does, and then what are all the types of database deployment. So we have actually automated the deployment for this tool, and then the components that we implemented using this tool for one of our clients. So we will talk about, okay, how to approach database deployment, what are the different types of database deployment, and then what tool we have used in order to do the automated deployment of the database changes. Okay, so then we will provide you the in detail introduction of the framework, and then we will also talk about what are all the different tools we have considered for CICD deployment, and what did we implement for our CICD pipeline. So those are the three main agendas we'll be talking about today. Okay, so what was the problem statement? Okay, so the clients had a problem where we had to ingest data at the same time where the tables getting ingested were getting queried. So the data was in the cloud, and we had to ingest data at the same time the data was getting queried in reports. So that was one of the problem that was considered. We need a database that would support that process. And then we need a development process where we can ingest a lot of tables quickly, because we had many number of data sets that needs to be ingested. So the process had to be, the ingestion process or the development process had to be accelerated. We cannot prolong this project for a very long time. So if we had to make it viable, they had to be done very quickly. So ingest data in real time with minimal tools. The data that's coming into the cloud was coming in real time, and then the querying was in real time. So the data had to be ingested in real time. So the new platform that we built was expected to be supported with minimal skills. So the clients did not expect a lot of new tools to be brought in order to build this platform. So they wanted everything to be contained in the cloud, so that the existing team and the skill set that's available within the organization can support the new platform that is getting built. So the input format was in JSON. So any kind of JSON format had to be parsed and then ingested into Snowflake. So semi-structured data ingestion was one of the problems. Automate the deployment process, because the client was looking at global deployment of this platform. So we had to automate the entire process, the ingestion process, and then the deployment process. Everything had to be automated. So we can't have any manual steps in deploying this solution. So that's one of the considerations. We should be able to roll back in case if there is something goes wrong, and then we should be working parallel, so because a lot of developers going to work and then develop different components. So we should have a rollback feature. So enable parallel development and then deploying the solution to different environment, as I talked about a global solution. Okay. So what are all the advantages of Snowflake? Why for this particular problem statement, why did we went with Snowflake? Snowflake was ACID compliant, so that means it had a strong consistency. So that means like when we are ingesting data, we could continuously read the table where we are merging new data without any problems. So Snowflake was good at that. On-demand scaling, so it's a true database for the cloud, so you can scale up and scale down as we need. So that was one of the considerations why we went with Snowflake. So cloud tools for integration with SQL code, so we can use Snowpipe to ingest data. So when you have the data in your blob store, you can ingest data using Snowpipe, and then you have external functions where you can't call external APIs like API gateway and then trigger external functions. So that was useful as well. So Snowflake provides stable streams. So that means we don't have to worry about when we are ingesting data from the same stream, you don't have to worry about what has changed in the source table. Snowflake provides the streams which you can tap onto and then create views so that you can ingest data without worrying about are you double querying the data or doubling upon the data that you are ingesting. Ability to orchestrate workloads. Yeah, again, you have store procs and tasks which can be used to orchestrate your workloads. So cloud cross cloud integration, so you can even directly query the blob store in another cloud when you are without being your Snowflake on the on the same cloud. So example, like you can query Google data while your Snowflake is residing on AWS. Handle semi-structured data, so it has a very strong parsing capability for parsing semi-structured data like JSON. So it has a feature called variant which can be leveraged to query JSON data. So we have used all these features in our tool. Okay, so what is Altis Snowstream? So Altis Snowstream is actually the ingestion pipeline, repeatable ingestion pipeline, 100% repeatable ingestion pipeline on any cloud when you have a Snowflake deployment. So if you want to ingest data into Snowflake, you can always use this pipeline. So it is a set of store procs that needs to be installed on Snowflake. So that will get you going. So it's a SQL only pipeline. So that means like it uses only SQL code and SQL store procedures in order to ingest the data. So it uses the power of Snowflake. So whatever I explained in my previous slide, it uses all those advantages, and all those advantages and the tools are built into this pipeline. It accelerates data ingestion because it is config driven. So for a simple data ingestion where you are mapping like one attribute to another, like there is no much transformation. You have a JSON document, a single level JSON document, and it has to be flattened into a table. You can set up the configuration. You can set up just configuration or the mapping table. The tool will take care of generating the code and ingesting the data. You don't have to write any further SQL or transformation. So we have also this package also includes the CICD pipeline. So we have automated the deployment of this tool. So whatever the components we develop on top of this tool can use the same pipeline in order to automate the deployments. So native support for JSON transformation. So we have already handled all the requirements of JSON transformation in this tool. Supports batch processing and streaming ingestion. As far as the data can be ingested into the cloud, when I say that data can be brought from any SQL or any API source into an object store like S3 or Azure Blob or Google Storage, if you bring the data into that particular location, it can be automatically ingested into Snowflake, where it can be in batch or it can be in streaming. ability to support complex transformation, though I said that for a single level transformations, no code is required, but the tool also supports complex transformation where you can provide a SQL code in order to do the transformation, where you are transforming one source or one JSON into multiple tables in the target. So that pattern is also handled in the in this tool. So handle multiple load patterns. So what I mean by that is, like you sometimes you just want to insert data as it comes. Sometimes you want to create an SCD2 type pattern where you want to expire old rows and then insert the new row. So that's handled as well. Easy customization. This tool is extensible. Like though I said that we are currently only handling JSON, you could extend it to handle CSV or XML or any other type of data, and then also we can add more ingestion patterns in the future. Okay, so let's talk about database deployment approach. Okay, so when we started on this journey of developing this tool and then the deployment approach for this tool, we looked at what are all the different ways a database can be deployed. So a database can be deployed in two ways. One is declarative approach and an imperative approach. So declarative approach describes how the target schema looks. That means like you develop a target schema, and then you use the target schema to actually do the deployment. In future, if the target schema changes for the ongoing deployments, you don't mention or you don't provide inputs as how that deployment has to be done. Example, like we add a new column, so that means you have to actually implement an alter statement to add the new column. But in a declarative approach, you don't do that. You just create the new column in your dev database, and then the tool, the declarative tool, takes care of comparing the target schema and the source schema, and then coming up with the script that's required to implement the change in the target database. That is declarative approach. So that you can see that describes how target schema looks. The tool will generate the scripts to change the target database. In case of imperative approach, the developers have to compile a change script and then also mention the order in which the change script has to be implemented. So in the first deployment, you may create a table. In the second deployment, if you wanted to add a new column to this table, you need to add the new alter statements to your set of scripts, right? So that's the imperative approach. So what are like declarative approach is very simpler and a very straightforward approach. Like you create your column in your dev, and then when you are going to production, use the tool to compare dev and production, which will give you the script that needs to be executed in production. But imperative approach is very complex because you have to maintain the order of the script, you need to version control the scripts, you have to know what scripts have been executed in your target environment, and then what scripts are new and what has to be executed, how do you roll back. So all of these things needs to be specified by the developers in the imperative approach. Unfortunately, we don't have a tool that supports declarative approach for Snowflake. So we had to go with imperative approach. So imperative approach is supported by tools like Squitch, Flyway, and Liquibase. So we have done an option analysis and then went with Liquibase. That we will be explaining that in the detail as we in the next part of the session. Okay, so what's the architecture of our data pipeline? The data pipeline, in our data pipeline, we have source systems here on the leftmost source system, right? And then the data from the source system is getting ingested into an S3 bucket using Kinesis streams. Once the data is in Kinesis stream, the code required for ingesting the data from S3 bucket into Snowflake is taken care by our Altis Snowstream tool. This Altis Snowstream tool takes care of creating all the infrastructure and all the code required to ingest the data and transform the data till the staging layer. So it uses Snowpipe to land the data into landing. Then it uses the table streams to detect the changes in the landing data. And then we have a set of store procs that gets executed every minute. That store proc then ingests data into the staging layer. Okay, so you can have real-time reports pointing to the staging layer in order to query the data, and then also use further tasks that will transform the data into data warehouse. So this is the simple representation of our data pipeline. And then also it highlights which part of the pipeline is supported by Altis Snowstream. So that's the introduction to our session today, and then a high-level overview. I will hand over to Mike in order to take you deep into the Altis Snowstream functionality. Thank you.
Thanks, Anand, and good day to you. Thanks for joining our webinar. Just gonna wait to flick across to the next slide. Okay, alrighty. So, as a developer approaching this Altis Snowstream, the purpose of this slide is to really just illustrate the three core processes that you need to be aware of and need to follow in order to get going with this tool. So up on the left-hand side, once off Snowflake account configuration, and that's things like the storage integration, S3 event notifications. I'll go into more detail about those in upcoming slides. Then there's a step to configure metadata, and that's an extremely crucial part to the setup. And then lastly is running the Liquibase update command, and Andrew will take you through that in more detail a bit later. But the key takeaways are it's really a three-stage process, and you don't need to be extremely familiar with what's going on under the hood. The main sort of developer effort is in this configuring of the metadata. Right. So some of the streaming framework features that are supported, like I said, metadata driven. So with metadata driven, what we mean by that is the stored procedure that's going to be responsible for ingesting this data from S3 will leverage those metadata tables to know how to interpret that incoming JSON file, and then how to what the data types are, etc., and how to write it into the staging table in Snowflake. So that's set up. Once that's done, that provides really all the instructions of how to interpret the incoming source data and what to do with it. There's also a code generation Python script that comes along with this, and what that serves to do is to allow you to generate a lot of all the components that make up this framework, using just basically, once you've configured the metadata, you then just call this Python script or this using CLI just for that specific object name, and it will spit out all the DDLs that are required that go into your repo, and that all those DDLs then get leveraged by Liquibase, pushing into the target Snowflake database. So the metadata driven, that happens first, and then you've got this nice handy tool that generates the DDLs, and that then is what gets deployed. So the load patterns that are supported by this are merge, insert, and custom. So by merge, what I mean there is like a slowly changing dimension type 2 scenario. So there's some tracking hash functions that come with this framework, and they'll use to identify differences in data and work out whether a row needs to be expired and a new row needs to be inserted, for example. And then you've got your standard insert only pattern. And then lastly, that custom, which Anand mentioned earlier. So you may have a scenario where an incoming JSON file, instead of a single sort of one-to-one mapping between a document and a staging table, you may need to output that single file to 4 different staging tables. And so you can specify your own custom SQL snippets in one of the metadata tables, and the framework will come along and use that SQL snippet to know how to process that incoming data. Then lastly, logging and error handling are supported features, and yeah, I'll take you through error handling as we go. One of the upcoming slides here. So in terms of required infrastructure, So in this example, I'm just using AWS S3 as the location where this incoming data is landing in an S3 bucket. And so there's some event notifications that get set up. And essentially what that means is as a file drops into an S3 bucket, there's a notification that communicates to the Snow pipe, and that Snow pipe will then do its thing, which I'll explain later. So essentially in the infrastructure setup here, you've got S3, you've then got a landing table in Snowflake. And that's all that really serves to do is to be a destination for the Snow pipe's copy command. So the Snow pipe will read from the S3 via a stage and place the data in the landing table in a CSV format. And the reason we chose to land it in CSV is that it gives us the option to actually cater for scenarios where a source system might provide badly formed JSON, and so we could handle that error scenario as required. Sitting on top of that landing table is an append-only stream, and Anand explained a stream earlier, and basically it's just a mechanism to identify a changed data set. So instead of having to use high watermarks and other features to work out what data is changed at source, this append-only stream is something that the main stored procedure queries to know what new data it needs to process through to staging. Stage. So this is really just the configured location of the incoming data in S3. And you also set that up specifying the file format. So we'll have two file formats that ship with this, and it's the CSV and one is for JSON. And then the Snow pipe, so all that's really doing is executing a copy command from the stage to the landing table, as I mentioned. So it does that once it gets a notification of a new file landing. Okay, then I guess the stored procedures that do most of the heavy lifting in this framework is one called extract stream object, and that accepts a parameter called source name. So for each of the different files that you may be receiving, you'd list out those in the metadata table. And now, say for example, you had 60 different incoming tables. For the first one, you'd set up the parent metadata table, and then the child or the attribute level metadata table, and then the stored procedure gets called with that source name for that incoming file. And then it does the processing of data all the way through from the landing table through to the staging table. Okay, and we also have an error handling stored procedure per source as well. So as I mentioned, say for example, we get a batch of data through, and there's some bad data in that batch. This the sort of principle is to siphon off that whole batch of data into an error table, and then an error stored procedure comes along and tries to process those rows line by line. And if a record can be processed successfully through to staging, it makes its way through to staging. But any bad data gets sort of segregated in that landing table and can be dealt with in that area. So it gets separated. So we clean out the bad data from the good data and allow the streaming process to continue without being held up by bad data. And tracking hash functions, as I mentioned earlier, those are used to identify any, as part of that merge load pattern, to identify any changes in records between what we already have in staging and what's coming in from the source. All right, tasks. So tasks are just simply a means to execute a stored procedure on a schedule, and we've got the error one. The main streaming object one on a minute interval, for example, to process data at low latency. And the error proc could be on a different schedule, maybe every 10 or 15 minutes, for example. Right, and lastly, the staging table. So that's just the Snowflake table where the data is ending up, and that's our destination for our ingestion process. So yeah, those are the key pieces of infrastructure required. This is really it sounds like a lot, but that automation of first of all, that Python script I alluded to will be generating a lot of this for you once the metadata is configured, and yeah, then the streaming process. This is a generic stored procedure, really, that is designed to interpret all that metadata and know how to process the different incoming files accordingly. All right, now this just illustrates what I'm taking you through in a diagram. So similar to the earlier one, we've got our cloud storage on the left here, and we've got data coming through either from batch or from streaming into an S3 bucket. We've got a storage integration sitting in between there, and essentially what that does is just support the security and the connection between S3 and between the Snowflake environment. And you've got that stage, which knows about the location of the incoming files in S3. And you've got a landing table, which is getting the new messages in CSV format. On top of that landing table, you have the stream, which is identifying any rows that are hitting this landing table that are being sort of placed there due to the Snowpipe being called and that copy command being executed, lifting data from the S3 into landing. Then you've got the main stored procedure that's going to run and read from the stream for any new sets of data that have come in, process the data into staging if successful. Anything goes wrong during that process, data gets siphoned off to an error table. And actually on top of that error table, we have a different stream listening out for any new errors landing on the table. Very same principle as before. And then another task executing the error, the sort of error stored procedure that's going to come and tidy up any good data that can be salvaged from that error table and place it into staging. Alrighty, development process. So keep mentioning that the metadata configuration is a core step required. And we have source level metadata. So for example, I've just got a dummy, think of this as a product, product code, product name, or product type attributes coming through in a product source file. So you'd configure one record in a source or sort of header level metadata table for product. And in this attribute level metadata table, this is really where all the development effort is situated. So you'd be writing SQL to insert into this metadata table for each of these attributes. So here you can see our source attribute name is product code, product name, product type, etc. And then the staging attribute names are named the same in this case, but they could be different. We also specify which of these attributes is the primary key, and then the staging attribute data types, for example. And then, lastly, just another note. This is an example of the CLI tool sort of command that you'd execute once this metadata had been set up. And all of those things like the stages, streams, the stored procedures for the staging tables, all that DDL that's required for this framework to work would be outputted by the CLI tool into the repo, available to be deployed by Liquibase. And I think that is it for me. I'm going to hand over to my colleague, Andrew.
Awesome. Thanks, Mike. So, so I predominantly focused on the CI/CD portion of this project and product. So in order to actually have a CI/CD workflow and spin up environments on a dime, we first needed a database migration library. So as Anand mentioned, there is actually no declarative tool out there yet available for Snowflake. But really, in effect, all these libraries do is just execute SQL. So we ended up on Liquibase primarily due to the features available in the free version and its simplicity. And its main use, as I mentioned in this project, is just to execute SQL against a database and track what's actually been executed so that the next time we execute it, or execute against it, we don't have to figure out where to start from again. And so in a nutshell, it really is just Git for database and its infrastructure. So Liquibase is used by a number of companies, as you can see on screen, AIG, NetJets, Nike, to name a few. And really, its features in relation to the main goal of our CI/CD framework is that it has the ability to automatically deploy into different regional Snowflake instances and accounts with potentially different versions of the same streaming framework. So I mentioned before that the main use of it in this project is just to execute SQL in a database and track what's been executed. And in doing so, it effectively locks in what has been executed. So for example, if you create a table and drop a column and then add a different column, the order of operations matter here. So rather than simply generating and executing the final state, and this is also what's called just modifying the database schema. So while databases are the single source of truth for business data, we also want a single source of truth for the infrastructure of the database itself. Really, what Liquidbase allows us to do in the end is deploy whatever is stored in the Git repository with a click of a button. And so this allows us to have a very convenient workflow for our dev team. So we really just follow a feature-driven development patterns. So what does that mean? So for example, we might have to ingest 80 tables to build ETL pipelines for those 80 tables. And for the sake of simplicity, let's say each table would be its own independent SQL file. So each feature would be its own branch. And because we're able to deploy a copy of the streaming framework from scratch with the click of a button, we would be able to create as many feature environments as we want. And each of those would be a replicate of the dev, test, and prod environment. So in other words, each feature branch could be spun up with its own contents, each feature branch having its own environment, allowing for all developers in the team to work in parallel without any dependencies on each other. So this approach gives us some key advantages. The ease of recreating bugs. So anytime anything goes wrong, each developer can recreate the exact scenario in which a bug is occurring through the development process. So if someone's testing on, let's say, the master branch or in the test branch, and there's some specific things in there that no one wants to be touched, I can just copy the entire thing and spin up the exact same logic, and then recreate that exact same scenario with a click of a button. So there's also obviously the parallel and distributed development. So if you have a lot of team members, especially if the team is remote, it enables a high concurrency of work while allowing team members who don't understand how CI/CD work to contribute to the project. Also for quality control, because this forces all the development work to be contributed against a Git repository, all the quality control goes through pull and merge requests. And so everything goes through at least two sets of eyes. And you have subject matter experts checking contributions at every single point in time. It also helps faster release cycles. So obviously with the standard best practices used in software engineering, smaller change sets are encouraged for faster development and faster deployment over large sweeping changes. And also it helps logically separate features for people like product managers or any other department like marketing. So we know when certain things might come out in terms of particular data coming in. So really at the end of the day, deploying just becomes as simple as merging into a specific branch. And in the case of our client, it might be various regions, and each region could be an individual branch to control the actual state of that deployment and a particular version of that of the code base. That's really it in terms of CI/CD. I think I'll hand over back to Anand if we have any closing remarks or any questions that we have in the audience.
Yeah, thanks for attending the webinar today. Yeah, we will give a moment for any questions. Yeah, if there is no questions at this moment, so we will conclude this webinar for today. So you will have the opportunity to ask us questions. We will be sending a follow-up. For those who have registered, we will be sending up a follow-up email and with the link of the recording of the webinar today, and they will have the opportunity to log any questions directly with the presenters today, and then we'll be responding to those questions as well. So thank you for attending today's webinar. Thanks.